Alright, I'm Jake Nicholson, and this is the return elevator group, return elevator sampler group. Jake.
I'm Jake Kindred.
I'm Mike Gregg.
Return sample elevator. On what machine is this?
This is being built for John Deere for their Class 7 combines, so like the 9770 combines, the new models.
Okay, and this is not, from what we're looking at, is not something that a farmer's going to see on his combine or her combine, but this is to enable them to do development or something?
Yes, this is just for research only. They're trying to see the maximum capacity of their machines. They're trying to push it to the limits.
All right. Okay, so I see some pneumatic cylinder, some electronic controller. Maybe you can start with the controller. Explain what's happening over here.
Okay, right here, here's our PLC, and currently it is...
What's a PLC?
PLC is a programmable logic controller. Right now it is not in the system because we're set up for demo right now, but this will run the slide that opens the bottom of the return elevator, and it will hold it open for a certain amount of seconds, and then it will close it for a certain amount of seconds.
The reason for doing that is once Deere takes the samples out of the bins, they can tell what the mass flow rate is because they have the mass of the sample being taken as well as the time that the door was open.
And then the actual bins move with just a normal 3-position switch on these solenoids down here. If you press it up, it goes up and it'll hold it in position, and then to take the sample, you slide it out, and then if it was hooked up to the PLC, it would shut back down after a certain amount of time.
Okay. So we've got electronic control of pneumatics with some mechanism here. So what were the special design challenges here?
Some of the design challenges we had to look at, this is obviously going towards the middle of the combine, so watching out for other fixtures on the combine, the tires. We had to work off of the ground clearance that we had off of the frame of the combine, and then you're also going to have a lot of debris in the field, so making sure that the design is robust to maintain a lot of that impact and debris that you're going to have moving around all the equipment.
These look like, are they stainless steel or aluminum?
Stainless steel.
Stainless steel. So no corrosion involved. Did you have to use any computer-aided design, graphics sort of thing, or did you just grab some steel and fold it up?
We used some Pro-E in modeling what we wanted the door to look like in the bins, so we had to have those manufactured out. But for the most part, a lot of it, we just communication, talking between each other, and we knew what we wanted, and we went from there.
So what would you say was the most challenging part of the project? Anybody can answer that.
I feel like one of the most challenging parts of the project was actually designing something that would sit in the space that we had to work with and not interfere with the travel of the rear tire, especially during turns. We originally had started out with a 3-bin design, and we went to a 2 because it saved us space, because when that rear tire turns in, it's liable to catch even now. But this is a lot more, it has more operability than the 3-bin system.
So why do you think your project is the best one we're going to see today?
Because it can run. It has actual interaction with what we have. You can see how the sampling would happen. We would demonstrate it with the grain, but the system's not set up for that right now, and there'd be a lot of debris and dust going around. But you can actually see how the sample would be taken with the system as it is now.
So here we are in the Department of Ag and Biological Engineering at Purdue. We offer degrees in Ag Systems Management and Agricultural Engineering and Biological Engineering. We're solving the world's problems one at a time.